All right, quick diagram lesson on glucose. So this is what glucose looks like. This is the simplified version, just a stick figure basically version. And I prefer these because they're a lot easier to draw. They take less time. They're less confusing for me to read. Some things you need to know about the stick drawing is that anywhere that two or more lines connect is going to correspond to a carbon. That's why they say, like, life is carbon-based life forms. So when you do your stick drawings in biochemistry, where two lines come together, it's always a carbon unless otherwise noted. So for example, right here, there's an oxygen at the top right-hand part of this hexagon shape. And that hexagon shape is called an aromatic ring. That is what glucose is as a molecule. So if you like it, then you should have put a ring on it. If you're sweet on a girl, you got to put a ring on it. So that's how I always keep that in my mind. Anyways, so these correspond to carbons, these little spots right here. And then where the legs come down, we'll call those like legs or arms. At the end that is drawn, that corresponds to an alcohol group, an OH group. And the other part that you don't see, by the way, this is where my dog snotted on it, sorry. The part that you don't ever see when you're looking at these drawings is where the hydrogens come in, because hydrogens are a people pleaser. They just float around in the atmosphere looking for somebody to take their extra electron that they don't need. And so they're just constantly giving their electrons to other people, and they're ubiquitous and necessary but kind of annoying. So in the stick drawings, we just don't draw them, okay? So like, for example, on this far left joint, we know this is a carbon. We know that at the bottom of this leg is an alcohol group. And there is an unspoken but recognized hydrogen right here, balancing that out. Because if you'll recall from the periodic table, carbon lives in the fourth column. That means it has 4 valence electrons to give. And therefore it needs to have at least 4 bonding points. Not necessarily 4 total. There could be double bonds or even triple bonds, but it has 4 electrons to give, so it needs to make at least 4 bonds. Well, it needs to make the 4 bonds in order to be considered happy. And if you want more information on that, I can totally send that too. Anyways, so this is our glucose molecule, C6H12O6, wham bam, thank you ma'am. Now, because I do everything ass backwards, I put the rest of it at the bottom of the sheet, so we're going to look at the bottom of the sheet next. Boom. When 2 or more glucose come together, this is called a dehydration synthesis, which is exactly what you would think it is. Dehydration is we're pulling water out like you're dehydrated, and synthesis means to make. So basically these 2 glucose come together, and remember we discussed before how at the bottom of every leg that is drawn, there is an alcohol group. This one is always drawn woogly because it can either go down or up, being if it was a beta or alpha shape respectively, but don't worry about that. It's whatever. So here's my 2 glucose skeletally drawn. I did stick the alcohol groups at the bottom just for clarity, but when these 2 alcohol groups come together, one of the alcohol groups will pop off and steal another hydrogen. So you'll have 2 hydrogen and 1 oxygen to make H2O. So every time these 2 bond together, you are removing 2 hydrogen and 1 oxygen. And in this process, this is what you make. So these are 2 glucose molecules now bonded together. And that water that pops off of there, the dehydration synthesis, she's gone. She's elsewhere. Don't worry about it. You can bring her back later to use water to dissolve these bonds together, which makes sense. Like that's how water dissolves sugar cubes, or like coffee, if that's what you're into. I drink my coffee black, but whatever floats your goat. I digress. Apparently I need more coffee. Yeah, so that's why when you take 6 of these, which you would think you would just have 6 times the carbon, 6 times the hydrogen, and 6 times the oxygen and put them together, that's not how that works. Because you have those 6 bonded together, so you have 5 joints in between them. So you would do your regular math. You would do like the, for the hydrogen, need to put it down on the thingy. You would do like the 12 times 6 makes 72, but then you're making 5 of these water molecules to bond them together. And each water molecule has 2 hydrogen. So you're pulling out 10 hydrogen total to make all that water. Where am I at? There we go. So you would subtract the 10, and that's how you get 62. I'm writing without looking. That's actually not that bad. Anyways, so yeah, that's how you'd figure out you'd have 62 hydrogen total after bonding all of these delios together. And you also would take away the 5 oxygen you need for the 5 water molecules, and 36 minus 5 is 31. So your final result when you're combining 6 of these total is you do still have the carbon. You never lose carbon in dehydration synthesis. So you have, need to find a space where I can see while I write. What am I doing? You have C, 6 times 12 is 36. H, 62, O, 31. Bam.